All right, so begin with this problem. We started how to set up an integral for volume using disks and cylindrical shells. Some problems you can only use one particular method. Some problems can use both, but they're not equally at the same difficulty level. Okay. For this problem, you may easily using the cylindrical shells to solve the problem. So let's draw the graph first. You have to draw the graph. This is part of the solution. Right. So you have this is a parabola, right? Y equals x squared. Here's another parabola, right? Opens downward. This is 3. Here's 0. So you have to find the intersection point. The intersection point have the same y value, so x squared equals 6x minus 2x squared. So I get, you can easily get 3x squared minus 6 equals 0, then x3, x minus 2 equals 0. So x equals 0, x equals 2. And the y coordinate to be 0, it's a 4. So 2 and 4. All right, so you shadow the intersection. Right, this is only portion of the graph. This is just 2D graph. I'm talking about the solid. So you have to draw the solid. Okay, its rotation. It's important. The reason I wanted you to draw it, because otherwise you don't know whether it's around about the x-axis or about the y-axis. Some students set up an integral. Look at the integral. This is for the volume of the solid obtained by generating the solid around the x-axis, not about the y-axis. So that's the reason I wanted to draw the graph first before you write down the formula. I don't know how to get a formula, but when I look at the formula, when I look at the integral, it's for the different solids, not for this solid. Okay, so this is let's draw it. It's like this type. Okay, that's probably enough. Another section, right? So it looks like a 3D. It's not needed to be perfect, but it should look like a 3D, right? So every child should learn some drawing when it was child. I think a majority of kids enjoy drawing, but at least they have to draw how do they draw? Have to draw the cup, right? And something like a 3D object. Okay, that helps you to draw the color. Right. So now, so the first method is going to be used. I don't know which method you're going to use, right? You're going to use disk. You're going to use a cylindrical shell. If you use a cylindrical shells, you are going to the first method. Okay, cylindrical shells. Okay, so I'm not going to use the same picture. I just redraw it again. Right. This is a picture. Okay, so this is okay. Cool. All right. So cylindrical shells, you're going to the axis of the cylinder is going to be the y-axis. So you use a circular knife to cut it, and what the cut piece is here. Right? Yeah, that is. And it's so the parameter is actually, this is a point you're going to use, okay? This is maybe the point, another point. So here's a radius R. Okay, this is H. The area of the cross section is 2 pi RH. Okay. But what is the parameter you're going to use? Use the R. Okay. So dr tells you the volume of this one slice. Dr is the thickness of the cylinder. Okay, and the integrate, R is going to be from here. This is point 2 and 4. R, the smallest value for R is 0. The largest part of the value for R is going to be 2. So that is volume, but that you have to express H. Well, we don't know the H. Just need to calculate H for that particular R. What is h? Okay, what is h? You have to figure it out, right? So actually, the h is going to be the difference. You see, this is a point x, right? Now, r is going to be x in this case. H is the difference of the two y values of the two graphs at same x. So the one on the top is going to be 6x minus 2x squared. That's on the top. It's parabola opens downward. The one at the bottom is going to be x squared. So the difference gives you the length of this vertical line segment, which is the h. Right? Now it's up to you if you want to use the x variable or use the y variable, because r is going to be x anyway, right? So so this is going to be 6 and 3 x minus 2. Okay. Yeah, x minus 2. So when x equals 2, h is going to be 0. Let's look at the picture. So you either still use the parameter r, then h will be 3r minus 2 dr. Okay, you don't need x. That's mutual. Okay, the variable is r. It's the original variable. But for this particular problem, you can use the x variable. Okay, because I equals x, no difference. All right. Then, second method. Second method, use disks. Okay, this is still parabola, and this is another parabola, and rotate about axis, y-axis. Okay. This time I'm going to cut the solid. Use a flat knife parallel to the xz plane. This is the x. We are in the 3D dimension, so this will be z-axis. Okay. Begin with a two-dimensional section, right? Region, and you rotate in the space. You go to three-dimensional space. Then you can rotate. Otherwise, you cannot rotate. Okay, rotate is generated to the solid three-dimensional space. Right? Even in high-dimensional space, because that piece is only two-dimensional. So if you travel in space, you only get three-dimensional object. Right? But you can go to high-dimensional space, but you can only get three-dimensional object because they only add one more freedom. Right? All right. So now we're going to cut it using flat knife. So you need to get cross section. Okay. Because this is yeah, let's draw the picture like that. Okay, this is a one cross section. Okay, let's go. In advanced mathematics, we do not use the y variable directly. We still use r. Okay, this is the distance to the yz plane. Okay, this is distance to the yz plane. Actually, what you're doing here is use a family of a plane to cut. Yeah, so the distance between you see, between these two will be r. Okay, right? Two planes. One is the fixed one, the xz plane. Another one, this x change. Right. So the cross section, in this case, the cross section is going to be, this cross section is going to be AR. Right. So the volume is going to be integral. Again, ARD. It's the same formula. Okay. R is start from 0 to 4 because the highest point you can get is a 4. See, this plane going up at that point is coordinate 2 and 4. Right, 2 and 4, the highest point it can reach. You don't need to go further. Right, so that's 4. But how can I calculate this? It's challenging, right? So I needed to figure out this. Okay. But this cross section, okay, those points, okay, let's see. For the same y value, see, this is the y value, right? Y. And here's the first one. So I'm going to, yeah, what is AR? AR is going to be this 2. You see, this is radius. This is R1, this R2. So it's pi R2 square minus pi R1 square. Because the difference, this 2 disks. I needed to figure out what's R1, R2 for the fixed Y. Okay. My R is just Y, because Y coordinate. Then I have to solve for R1. R2 is easy. R2 is because this is a graph, right? Y equals x squared. When Y is fixed, R2 is going to be square Y. Okay, clear for fixed Y. How about R1? R1 is going to be, we have the equation. Where's the equation, right? It's going to be Y equals 6x minus 2x squared. So I have to, for the fixed Y, I have to solve for x. So x squared minus 6x plus Y equals 0. So x is going to be, this is 4, 6, plus minus negative 6 squared minus 4ac. Okay. You get, yeah, you can simplify, but I'm not going to do that right now. Just put this. So you have a plus minus. Why you have 2? Actually, you have 2 solutions. We will choose a negative one. As the reason is there's only there are 2 solutions. We only need the short one. So R1 is going to be 6 minus. Okay, it is more complicated. Yeah. For the fixed Y, let's look at the 2-dimensional picture. It's maybe much easier. This is a picture, okay, and this is a Y value. This is a R1. Okay, here's another one. So when you solve it, right, for the fixed Y equals 6x minus 2x squared. You are going to get 2 solutions, plus minus. So R1 is the one using negative sign. Okay. So now you put it back. So the volume is going to be integral from 0 to 4, and the pi R2 square, yeah, square Y square minus R1 square. Okay, so this is yeah, this is going to be the solution. Okay. Let me check which one. Yeah, first, yeah, it's 1 now. Okay, so R2 square minus R1 square. So you see more complicated, right? So here clearly indicates the first method is we're looking for. Okay, cylindrical shells do have a disadvantage in some problems to set up an integral. Okay. And a similar problem like this, here's the region is bounded by this, and the location is about x equals 5. You see, this is another vertical line, x equals 5. So when you draw, first of all, you draw the region, y equals x, right? X equals 1/2 of x equals 2y. So the intersection point will be again, here's 4 and 2. Okay. So this is two graphs, right? Y equals half of x when x equals 4, y is 2. Okay. When x is 4, y is 2. Yes, this is the intersection point. And then this is a 4. This is line x equals 5. So when you rotate about, okay, above this line, it looks like that, right? It looks like that. So how do you set up the integral for the volume? I think that clearly it's better to use a cylindrical shell. If you use discs, you get 2 discs. You have to take the difference, you know. But both okay. In either case, I think the formula is pretty similar, simple. Okay, the first method use cylindrical shells. If you use a cylindrical shells, okay, this is a cylinder you are going to get. Okay, this is cylinder you're going to get, right? Because the solid is the region generated by this region. So that's why you only get this cross section. All right, that's the first step. You draw the graph. Second step, the cylinder shares a radius r, right? And we want to, write down the formula. All right, it's AR dr. AR means this cylindrical shell, the area of the cylindrical shell. And R is the radius. How big of the radius? I think R is between 0 and 4, because when you enlarge cylinder, almost the radius is 4. The shrink to here, the radius. No, the radius, the smallest value for the R is going to be 1. Okay, so R is from 1, because this is a 1. From here to here is 1. Okay, and then from here to here is going to be 5. This is a 5, right? Right, 5. So I is between 1 and 5. I is between 1 and 5. So what is the ARH? It's 2 pi. What is area? 2 pi RH. So needed to figure out the H. So H is in terms of R, right? This is R, right? This is R. So here's a point. So for the same point, for the same X, okay, I think R is going to be 5 minus 6, right? Here's a 5. Right? I is going to be 5 minus 6. What is the H? H is the difference of 2 y values. If that you could express in the x variable is going to square x minus half of x, because the y equals half of x. Okay? Then it's up to you whether you're going to use x variable or use r for the integral. If you use r for the integral, you don't need to change the integral from 1 to 5. So what you have to do is you solve for x. X is 5 minus r. So in this case, h is going to be square root of 5 minus r, half of 5 minus r. So when I put into the above formula, it's going to be from 1 to 5, 2 pi r, 5 minus r, minus half of 5 minus r. Yeah. Okay. But if you want to use the x variable, x is going to be 5 minus x, right? I is going to be 5 minus x. So it looks just actually just should use substitution here. So di equals negative dx. So when I is going to be 1, x is going to be 4. When I is 5, x is 0. 2 pi, I is going to be 5 minus x. 5 minus x is 5 minus I is just x, right? And then half of x. And then this is the negative. So you can also express in this form. You can evaluate this into at negative. So that 2, you can use x variable, you can use r, okay, to set up an integer. X is from 0 to 4. Well, if you use a disk to set the integral, I'm not sure, maybe even simpler. Okay, you y is from 0 to 2. Y is from 0 to 2, and x. Yeah, let's see. This is a formula, right? Okay, y equals half of x. X, right? Here's y equals square x, right? So if you use the disks, what do you get? Right, this is a disk, right? And here's a point, a 4 and a 2. No, this is not 4. This is a 5, right? And this is a point, 4 and a 2. Okay. So you use a disk to cut. Actually, the disk is going to be the cross section of the solid with a plane. The plane looks like that. Okay, and another plane is at the bottom, the YZ plane, XZ plane. This is Z, this is Y, that's X-axis, right? So you have a 2 plane to compare. Okay, so there are 2. This is a plane at the bottom, you know. And here's another plane. Okay, so this is a 2 plane parallel to each other. And you get a cross section. It's interesting color. All right. So you get a cross section there, and you can use the y variable directly. This is a y variable. Here's y. This is y variable, right? But the y variable tells you the distance between these 2 planes. Okay, the distance between these 2 planes. So if this still r, that is going to be the AR, the area, right? The volume is still going to be AR dr. I is from 0 to 2. Okay, that's the original formula. You needed to figure out, figure out the radius. This is R1, this is R2, okay? So AR depends on R, but this is going to be actually pi R2 square minus pi R1 square, okay? So the 2 disks, right, each has a radius R1, R2. Now the only problem is how do you express them? If they can express it in terms of r, that's fine. But look at this fixed y here. R is going to be y, right? No problem. And what is R2? R1, yeah, R2. R2 is going to be y minus the x coordinate at that point. So it'll be 5 minus that x coordinate is y squared because y equals square x. So it's going to be y squared. Okay. Then how about R1? R1 is 5 minus x coordinate at that point, which is going to be 2y. Okay, for the given y. Okay. So now it depends. If you want to use y variable, use the x, use r. If you want to use r, this is going to be pi r squared, 5 minus r squared and squared. And here, 5 minus 2r squared and dr. Okay, but you can also use y variable because r equals y. Done. All right, so you set up 2 integrals. All right, so you go over this when you get home. Okay, those are the problems will be on the test. So today we are going to talk about section 5.4. What? Okay, and the simplest case is we try to move a box from here to here at the horizontal distance. Okay, so it's by constant speed. The force you're acting on F is constant. Okay, pushing that, and distance it travels is d. Okay, d is the distance it travels, and the F is the force. Okay, we found out F times d is a good measurement for the work done in moving this object from one point to another point. Okay, so so work if is going to be force times distance, assuming the force is constant, just acting on the box. Suppose you're going to pay someone to do the job, just moving from moving the box from one point to another point. Okay, and of course they're going to say, it's easy to move or difficult. You're going to pay more, right? So the pay should be proportionate to the work. So how to measure it? Just how much force acting on that object and how much distance it travels and do the product. That's a good measurement. Okay. So this is we define to be the work. So unit. The unit here, force can be used like a pounds. There are many measurements for the force. The distance also, there are many measurements for the distance using distance, right? Metric system, right? Using meters, using inches, feet, all kinds. Because we human beings lived in different place, different location for too long, isolated. So that's why we have a different languages. We also have a different measurement system. Okay, it's too late to make any change. Honestly, even in the United States, for example, we prefer using inches, feet. In other countries, probably don't do that. So it's very hard if you work for some companies, export stuff to other countries like furniture. 3 feet to you is standard, it's integer, but to them, it's a ridiculous number if you change it to the meters. So that table in other countries is slightly different, maybe a little bit higher than that. Okay, not like that, because we here use the integer. So okay, this height, the measure, the height. Okay, so It's harder if you have a manufacturer to making products for other country exports. The most headaches, the units. Okay. Even within the United States, some projects we have to use meters, some projects we have to use feet. So there are some companies making the parts for NASA. Okay, because the company, small company, the engineers just forgot the units. They made mistakes on the unit. Okay, and destroy the whole equipment. They can't find out. So this is unfortunate because many companies the measurements use inches, feet, but some projects from like a joint venture like it was UK, and then the blueprint of the equipment is using meters, centimeters. Yeah, be very careful. Okay. All right, so let's do this. Okay, now what happens if when you push the box along the line, right? You find out the ground is not flat, it's not smooth, thin. Sometimes it's very light. Some you don't need to push too hard. Sometimes you have to push very hard, right? And then so the force will be a function instead of a constant. Okay, so this is the question. Yeah, use the same moving the same box and travel and this coordinate line. Okay, and here's A, here's a point B, and you move the box to here. But when you acting as a force, you acting on that is going to be the function of x. It depends on It depends on it depends on the direction, the position of the box, because the conditions are quite different. Okay, the conditions are quite different. Yeah. So this is a coordinate line. Yeah. So here's the object. Okay. So the force acting on that is, it depends on the position. Okay, so you cannot simply say F times distance. The distance B minus A, right? The distance. But the work done by pushing this box from one point to another point is a number, not a function. The question is how do you set up the formula, right? Yeah, how do you set the formula? Because this function is continuous, right? I know the distance D is going to be B minus A, no problem. You cannot just simply say F times D. F is not a constant, right? Then here's the calculus idea. So that's the reason we want to understand the calculus idea to set the window, because in the future maybe you have to deal with another problem. You have to write a manual, like maybe you have to figure out formula by yourself. It's no formula in the textbook. Okay, so now you have to use this calculus idea to figure out formula, and right, then you can write a report that kind of says. So you have to do that. What you do is you divide this interval into many subintervals. Okay, so it's going to be A equals x0 minus x1, xn, and b. Okay, and over each interval, you can assume the force is constant. Okay, so step by step, if you push the box, okay, if you push the box from here xi minus 1 to xi, the box from here to here. Okay, the work is done by pushing the box from this point to the next point. The distance is clear. This is delta xi. The force is almost constant because when it's curves. Okay, so work done is going to be almost f of xi times delta xi, right? Or xi star. Doesn't matter what you choose. So this is an arbitrary point xi star, right? Okay. So you pick up arbitrary point and look at the force. But that over that small interval, all force is almost the same as like this. All right. So the total force is going to be sum of them, because you can push the box step by step, right? For n steps, each step, the force as the work done by pushing the box from this end point to the next end point is going to be the product of this. That xi is exact value, but this is an approximation because the force changes, but does not change it too much. We can say it's almost equal to the force at that particular point, xi star. And what you get is exactly the Riemann sum of the function. Okay, this is a Riemann sum function. And if you take the limit, okay, if you take the limit, this is going to be integral of the function, just dx. That. So we don't just memorize them because case by case, different problems. But that's what we get here. All right. For example, the force at the particular point is going to be yeah, we can assume that it's going to be x squared. Okay, so that means x is between 0 and 1. So that means when you push the box from one point from 0 to 1, you have to increase the force quickly. It's not the proportion to the distance. It's just increasing pretty fast. Okay, because x squared, the number is getting not quick. So we can use a unit. This is the force is in pound. This is x is in meters. Okay, in feet, usually in feet. If we use a pound, then use feet. Okay, in feet. Why? Because this unit, it's only must be used in countries like United States. Okay, if we use meters, then we have to use a kilograms instead of pound. Okay, that we have from the same kind of measure systems. All right, so now the work done by pushing the box from here to here is going to be integral from 0 to 1 and x squared just dx. So it's 1/3 x cubed, just 1/3. Now how do you write the unit? If you don't have a specific name for that, create a name for that, then you just say pound feet. That's it. Okay. I don't know. It's pound foot. So this is a this is a unit you can use. Yeah. Make it simple. Okay. So that's it. Now, sometimes the force is not given the information. It depends on the condition, the environment, right? So you have to figure out the force. You have to figure out the formula by yourself. Okay. This is here's a question. A very good question is, right? You have a tall building. Okay. So this is a stream. Nothing here, none that. Okay. You're trying to pull this up, but this cable itself is heavy. But when you pull the cable up, right, and slowly get it light because it's short. That's it, right? At the very beginning, yeah, it's pretty heavy. The cable is about 2 pounds per feet. Okay, 2 pounds per feet. Initially, this is a 50 feet long cable dropped from top of the building. Okay, find the work done to lift this cable to the top of the building. Okay, so you're not given the information on the, you're not given the function x to lift the cable to the top of the building. So here we are solving the problems. It's quite different from Math 153, the high school maths, right? It's unit K. Right. So you have to, of course we use machines, but just this example, right? All right, how do you do this problem, right? Maybe if you did lots of problems, maybe you already memorize the formulas. But let's try to figure it out this specific formula. Specific problem. I'm going to choose a coordinate system, coordinate line. You have to choose a coordinate line. Doesn't matter where's the origin. Okay, the integral may be different if you choose a different origin of the coordinate line. So the line should be going like that, right? You can go upward, downward. This is a coordinate line. Let's try this. This is 0. This is a 50. I prefer like that. Okay, going down pointer, right? So begin with a 50. Yeah, from 0 to 50. Because 50, this is the initial position. This is, it's not a one point. It's not like a box. It's not a box. When you lift the cable, it's not a box. Okay. So how can I do that? So this time I'm going to cut the cable into many pieces, separate. Okay. So divide. You still use the coordinate 0, x0 less than x1 less than x2, xn equals 50. Okay. For each interval, that piece, okay, that piece is going to be, how heavy of that piece, how heavy that piece determine how much force you need to lift that piece to the top, right? Of course, we're not going to cut the cable. We just imagine they have this cable consists of many pieces. It's no difference, right? And each piece, the length of that piece, the ice piece, okay? The ice piece, the weight is going to be okay. The length times 2 pounds. 2 pounds per foot is the density of that cable. So delta xi is going to be, of course, delta xi is going to be xi minus xi minus 1, right? All right, so that is the weight. If you want to lift that piece to the top, what is the distance it travels? The distance, the ice piece, the distance have to be traveled is about, because there's this piece, it's about xi, right? Xi is the coordinate of that particular point. There's no error here, right? Xi minus 1 xi. So I just count xi. right? So this is going to be xi minus 1. So xi is the distance it travels. Okay. So to work then to lift the ice pieces, Wi is about the weight, the force, because this is the force, right? Delta xi times xi. So it's going to be 2xi delta xi. Okay, the total force, total work, W is going to be sigma I from 1. Okay, so it is about 2xi delta xi. And then after you take the limit, it's going to be integral from 0 to 50 2x dx. This is x squared from 0 to 50. That's a 50 square. Okay, 2,500. And this is a pound feet. Now, if I see all the stuff, when I grade your exam, I will say, oh, this student fully understand the problem. That's perfect. If I only see this integral like that, get answer, then I don't think you understand the problem. I just say you're lucky, just put integral like that. Okay? You maybe just memorize this type of problem. Okay? But you have to explain to me how to do this. Okay? If I see the picture, yeah. So that means if you can draw the picture, the graph this, then I think this you're capable to solve as a problem, not this particular problem. Okay? Yeah, if I just only see the right, maybe I have a picture, but just give me the integral formula, somehow it gets figured out, right? Then it's harder to tell. You are able, you have this, you are able to solve as a similar problem. Okay, so that's a difference. Okay, let's see. Here's a problem. All right. Let's do one more problem. So here's a cone-like container. Okay, there are lots of water here. Okay, the dimension of this is a 4 meter, and this is going to be 8 meter high. Okay, now 10 meter high. This is water, right? So the initial level is going to be 8 meter. Okay. Find the work required to empty the tank by pumping all of the water to the top of the tank. Okay, so this is a question. There's no formula you can use it. Okay. By pumping all of the water top of the tin. Okay, I know the density of the water is going to be 1,000 kg per cubic. Are you sure we get an integer? I never measured that. So 1 cubic meter, what is about 1,000 kilograms? That's interesting. So maybe it's true. This is how do they define 1 meter long? I use the water, right? How do you have to define how long 1 meter, okay? Right, and then all over the world to use that. Otherwise, you don't know. Like 1 meter here in the United States is longer than 1 meter in UK to the calculate, right? You have to then. But the question is, you have to define how long 1 meter, right? And you can use a watt, right? Let's measure it. Make sure 1 cubic meter, right, is going to be 1,000 kilograms. That's also the way you can design. Like if you already define a kilogram, maybe you can define the meters. Okay, this is how do you, because then you make the relationship easier among those measurements. Okay. Then we have as a unit for the volume, like a gallon, very popular, right? And liters. Yeah, I believe that eventually, in the future, we will have the same measurements for the volume, same language. Maybe English would be the same. Okay, because it's communication, people travel around, right? And the same skin of a color, somebody even predict the future. Because time goes to infinity, right? Like T goes to like 1,000 years, 2,000 years later. So nobody knows. But the history is very short, even. We cannot even imagine what happened like 3,000 years ago. Okay? It's a very short time, but all the information almost lost except for some stones you can find out. Okay? So let's look at this problem, right? And I cannot use any formulas quickly. I just write on the integral. Nobody can do that. I forgot. Okay, right? What kind of, right? You have to choose a coordinate system first, the coordinate line, because different coordinate line gives a different integral. Result will be the same. Right? The coordinate line you can fix. Usually either as this is origin or that's the origin, doesn't matter, right? Now this time I'm going to choose this way. How about like that? This is origin. Okay, this is a 10, and here's 8. How about this? Okay. And we use a calculus idea or Riemann idea, Riemann sum. Remember, right? It's a Riemann idea to empty the water. The water is going to be going up, right? You just lift to the top and go up. All right. What I'm going to do is I still divide this interval into many subintervals. So it's the same idea, 0 equals x, right? Arbitrary partition. Okay. Then I look at each interval. The corresponding slice will be this. Right, so this is one slice. Okay, this slice, I have to figure out the radius. And I have to figure out the volume of the slice. Okay, the thickness is clear, right? The thickness is going to be delta xi, which is xi minus xi minus 1. And how heavy of it is. So the ice piece, you see, ice pieces. Okay, the weight, okay, is going to be the volume times the density. Okay, the volume is going to be the radius. Now I have to figure out radius, right? It's going to be the radius. What is the radius? The radius determined by this point xi. So I'm going to draw the picture here. Okay, so this is a radius. If this is a x, okay, and this is a, if this is a 4, that is going to be 10, right? So use the similarity of triangles. X over 10 equals R over 4. So in other words, I equals 4 over 10x, which is 2 over 5x. Okay, 2 over 5x. So at the point xi, right? At the point xi, so the volume is going to be pi r squared, right? The weight is about pi r squared. R squared is going to be 2 over 5 xi squared, and times delta xi. But that's just a volume. The density is at times 100, 1,000 kilogram. So that gives you the volume times the density gives the weight of that piece. Right? This is just the radius. Why did I equal? Because it's just rough estimate. Because so really the volume of this, it looks like a cylinder, actually it's not like a cylinder, it's special portion of the cone. So the radius, okay, the radius is almost equal to 205 xi. Okay. All right, so then the distance it travels when you lift that piece is also about that piece has thickness. So you don't know which is the point, right? But it's also, you can see that how far it travels. This is a xi, right? And from here to here, xi to 10. So that should be 10 minus xi. Okay, so that is the distance it travels. Then the work done to lift the ice piece, right, is going to be the product then. So pi 2 over 5 xi squared delta xi times 100, 1,000, and the times 10 minus xi. Great. All right. Once you finish that, the rest of them is simple. So total force, the total work is going to be sum of that. It's about, and then you get the Riemann sum. Let's write down that's 200 pi 1,000, 10 minus xi, and 2 over 5 xi squared delta xi. I put the delta xi at the end, and that gives the dx when you go to U. So finally, if you take the limit, okay, you should get identity. So this is from x is from 0 to 8. Pi 1,000, change xi to x, and 2 over 5 x squared and dx. Wow, now I did not know this is what we get, but this, we get that because yeah, we get that because we that's what we derived from the formula. Okay. Idea is very simple, calculus idea. Cut it in slides. Okay, and then move each slide from one location to the target. So yeah, it's what is liquid, but you can imagine it's just solid, right? Liquid can be solid, just like ice, you know. right? And then you lift, yeah, that slides. Imagine this is just no difference, right? Pumps the air out or lift the solid to the top. Just cut it into many slices, and yeah, but it's a little bit difficult to estimate the volume of these slides at the location xi. Inside the ice at the end point of the ice subunit, that side should go up, then lift it up. Okay. So I think the difficult part is to figure out the relationship between x and r. This is similarity of triangles. Okay, then you find the once you find the r, then you can use that to find the area of the disk. Okay, now yeah, find the area of this, then you can then you find the volume of the disk, then you multiply by the density, you get the volume, you get the weight of this piece. Okay, and this is the force you have to use to lift that piece all the way to the top. Okay, and so it looks complicated, but this is an integral, still very simple function. Okay, so we discussed 3 problems: how to set up the integral for the work done by lifting some object, okay, or move the object to one place to another. We always use a calculus idea, divide it into many pieces, and then you look at each piece, and you look at each piece to change it. All right, let's look at one more simple problem. Okay, here's a cylinder. Okay. So, cool. All right. So this original one is going to be 20 centimeters, okay? And we have here's a 30 centimeters box. My question, let's do a simple one. I understand this idea. My question is, find the work required to empty the tank. Okay, the water should go up, pull up. Okay. The radius of this cylinder, it's going to be 10 centimeters. Okay. Set up an integral for this problem. The density of the water is still 1,000 kilogram per cubic meters. 1,000 kg per cubic. Please set up integral. Yeah, this was a problem. Second test. Oh. Let's do this problem. Okay, I don't remember this formula, right? The integral. We have to just set up an integral. The idea is to draw a coordinate line. You know, yeah, it doesn't matter where you choose the starting point. Maybe this is origin, and this is y-axis. Okay, along this line, so you can call it x. Doesn't matter. Okay, so here 20. Now we use centimeters. If you use yeah, be careful when you change it to the you know, this density unit. Okay, so it's up to you. Okay, so the density I just simply call the rho. If you change it to kilogram to centimeters cube, for example, you can figure out the number. Okay. Yeah. So now, still, right? Right. This is a partition, and then for each slide, right? For each slide, you want the this is slides. Right? You want to lift it. For this slide, the ice piece, okay, the volume, how heavy it is, let's figure it out. you don't need to estimate. Actually, it's going to be the volume. Pi, I is always 10, right? Pi r square times the thickness, delta xi. That's the volume. The density is low. That tells you how heavy it is. Rho is the density, okay? Now, how do you change it to the density? Kilogram, 1,000, right? Times 1,000 G, right? Divided by 1 meter is going to be 100 centimeters. So this is cm cube, right? How many zeros I can get? 6,000. It's a 1, right? 1 kilogram per cubic centimeters. Okay, so 1 kilogram is going to be 1,000 kilograms. So 1,000 times 1,000, you have a 6 zeros there. Okay, then 100 cube is also has 6 zeros. I think this just simply just the density for the water is just 1 kilogram per cubic centimeter. Okay. Anyway, so this is density function. Doesn't matter what liquid you're going to use, and then the distance it travels is going to be, that should be estimated. That's going to be on the top is 30 minus xi, right? Because this point is xi minus 1. Okay. Then wi is about the product of those two numbers. Okay. Then w is going to be the sum of this. Is going to be estimate pi 10 square delta xi rho 30 minus xi. And after it takes the limit, it's going to be integral from 0. I think it's 20. It's going to be pi 10 square rho and 30 minus x and dx. Delta x becomes dx. So that's the form. Okay. That's all for today's class.